Hello, I am Karila Palma Silva. I will present the work entitled Methods for Comparing Execution Time of Different Input Data and Real-Time Tests on Complex Computer Architectures, developed by me, Luís Arcaro, and Romulo Silva de Oliveira. This presentation is divided into 6 main topics: a brief introduction, a description of the experiment environment, the presentation of our proposed methods for comparing the execution time of different input data, the presentation of an evaluation of the measurement method's reliability, the results obtained using a generic algorithm to select input data, the conclusions achieved in this work. Introduction. As computer rules proliferate in our society, system time requirements is known as real-time systems becoming ever more common. Design such systems require worst-case execution time or WCT analysis for determining other test needed time constraints. At the same time, modern systems demand for increasingly complex software, requiring more powerful and complex hardware platforms. Many of today's industrial equipment with a million of lines of code and of use Linux-based unbiased controls make WCT analysis an increasingly hard and important challenge. Real-time tasks executed on complex computer architectures suffer large difference from other activities executed on the same system, hence generate noise in the observed execution times. In this context, it is difficult or impossible to determine the worst scenarios for test measurement-based temporal analysis, that is, the hardware state and the execution path that generate the longest execution time. The main sources of temporal variability are the hardware of the processor used, the test control flow, that is, execution path, and operating system effects. Thus, the hardware effects and the execution path depend directly or indirectly on the input data used. The determination of input data is a critical issue for the time analysis of a test through measurement. One possible approach for finding the worst-case input data of the test with respect to its execution time is by employing optimization algorithms, such as generic algorithms, which often require the comparison of execution times. The large time variability observed in complex architectures hinder the comparison of execution times obtained using different input data. In this work, we propose and evaluate measurement methods capable of minimizing effects generated by the hardware platform input data comparisons, with the object of identifying which ones enable to compare different input data with respect to the generation of long execution times. We then implement a generic algorithm which its definiteness function is based on execution time measurement selecting use both traditional and novel methods, showing the relevance of the measurement methods for input data analysis. Experiment environment. The environment used in this work to conduct experiments is based on a microcomputer with an Intel Core i7 processor running the Ubuntu operating system with the vanilla kernel. Execution time is measured using the perf tool, an integrated collection of commands for inspecting internal kernel events. The software test used is the bubble sort. In this work, we consider 4 different input data for the evaluation: fixed loss sort integer array, which we refer to as sortage; fixed loss or reverse sort integer array, which we refer to reverse; and 2 randomly generated fixed integer array, which we refer to as fix1 and fix2. Methods for comparing the execution time of different input data. The 6 measurement methods evaluated are: single measurement, SN, consider only the first measurement of the task execution time. Block average, B average. Calculate the average of the blocks of 15 measurements of the task execution time. Block maximum, B max. Consider the max value observed within a block of 15 measurements of the task execution time. Block minimum, B min. Consider the minimum value observed within a block of 15 measurements of the task execution time. Multi-block maximum, NB max. Consider the maximum execution time observed in 3 executions of the task from 5 different starts. Multi-block minimum, NB min. Consider the minimum execution time observed in 3 executions of the task from 5 different starts. We perform evaluation in this work that can check distinct aspects of the proposed method. First, we evaluate the consistency of the methods. For that, we use identical distribution statistical tests. A method is considered consistent and it produces identically distributed measurements for the same input data, and it is considered inconsistent otherwise. According to our evaluation, SN, Bmax, and NBmax are inconsistent. There are doubts regarding the observation coming from the sum distribution, since they produce p-value of present tendency to low values. And B-average, B-mean, and NB-mean are consistent. Statistical test results are acceptable, since the weak p-values generally present tendency to high values. We also evaluate the measurement method's representativeness for comparing input data by assessing the probability of correctly concluding that execution time obtained with input X are greater than or equal to input Y to pointwise comparisons. For that, we compare 1,000 measurement taken use input X with it of 1,000 measurement taken use input Y. Total mean comparison with it referred to as direct execution time comparison. This table summarizes the result of direct execution time comparison analysis. According to our evaluation, the SN, B-average, B-max, and NB-max methods are unrepresentative. The mean representative in comparison to SN, B-average, B-max, and NB-max. NB-mean is representative. We highlight that NB-mean proves the most suitable among the methods evaluated in this work for the considered purpose. Measurement methods reliability evaluation. To verify the reliability of the comparisons performed using execution time measurement produced through the methods evaluated in this work, we collect samples of minimum execution time using the reverse, fix 1, and fix 2 input data. The samples histograms are present in the figure. By comparing the most frequent values produced by the inputs on such large samples, we conclude increased confidence that execution paths induced by fix 2 are in need of longer than to produce used by fix 1 and reverse as input data. NB-mean minimizes system noise and hence allows reliability comparing input data with respect to the produced execution times. Use of generic algorithms to select input data. For comparison purposes, use SN and NBME in generic algorithm to find input data that maximize the execution time of the test. In the performance test, use an initial population of 10 individuals, which are input data array, are generated randomly. We use as fitness function the execution time obtained use the SN and NBME measurement method. We also impose a limit of 10,000 generation for the generic algorithm as stopping criterion. The GASN input data present the long execution time obtained respectively by comparing execution time within developer generic algorithm to the SN and the NBME. The results of the direct execution time comparison analysis show that GANBME is greater than or equal to GASN in approximately 95% of the pointwise comparisons. This evaluation indicates that the generic algorithm was capable of finding a worse input using NBME in comparison with that found using SN. Conclusion. In this work, we propose and evaluate methods for comparing the execution time of different input data on complex computer architectures. Our evaluations show that the SN, the average, the max, the min, and NBmax methods are unreliable to this proposal. On the other hand, NBmin was capable of disregard effects generated by the complex hardware platform input data comparison, enabling more trustworthy comparisons. This is evidenced by the fact that the input data obtained through the generic algorithm used NBmin was worse than that obtained using SN. We hence consider this work's main contribution is the NBmin method. However, we highlight that this work's conclusions are specific to the test and the hardware used, and that experiments on other scenarios should be done to confirm the results. Thank you for your attention.